In this section, we're going to look at how we can find our tangent lines to polar curves. Because we can have a polar curve that looks more circular-like. Most polar curves are going to look like they have a circle shape to them, and then they might have something extra, like an extra loop. But for each of these points, there is still a tangent line. So we're going to see how can we find that tangent line? How do we find the derivative dy dx? Now, how do we find that tangent lines back in our Cartesian coordinate system? So a reminder from previous sections, to convert between polar and Cartesian, we have the equations x equals r cosine theta and y equals r sine theta. And pulling an idea from parametric, a couple sections back, if I want to find the slope in Cartesian, we need to find the derivatives with our new introduced variable in terms of our theta. So we're going to take the derivative of y in terms of theta and the derivative of x in terms of theta. So looking at our variable expressions we have up here, x equals r cosine theta. That means dx d theta, our derivative in theta. Well, there's now these two functions. There's r, which is r equals f of theta, and there's cosine theta. This is a product of functions, meaning we need the product rule. The derivative of r in terms of theta is dr d theta. We keep the cosine the same, plus now we keep the r the same and take that derivative of cosine. Derivative of cosine is negative sine. And simplifying this down, we have that dx d theta is dr d theta cosine theta minus r sine theta from using product rule. Same thing would go for y when we take dy d theta. There is a product, the function of r in theta and sine. So derivative of r in theta is dr d theta. Keep the sine. Plus, keep the r and take the derivative of sine. Cosine theta. Filling those in, we get a formula for ourselves that if we want to find dy dx, we're going to be finding dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta, using our two expressions from taking the derivatives of x and y. So now taking a look at an example, suppose we have the polar curve r equals 1 plus sine theta. We want to find the slope of this polar curve at theta equals pi over 2. So dy dx at theta equals pi over 2 is going to be filling in this formula from up here, dr d theta sine theta plus r cosine theta all over dr d theta cosine theta minus r sine theta at theta equals pi over 2. Well, we know r is 1 plus sine theta. dr d theta, the derivative of r with respect to theta, well, dr d theta, the derivative of 1 is 0, that goes away, and the derivative of sine is cosine. So that means this dr d theta is cosine. Filling those pieces in, we get cosine theta sine theta plus 1 plus sine theta cosine theta all over cosine theta, or cosine squared theta, minus 1 plus sine theta at theta equals pi over 2. Quick reminder, at theta equals pi over 2, all of our cosines of pi over 2 will be 0, and all of our sines of pi over 2 will be 1. So anything with that cosine will become 0. So this is 0. This is 0. Our numerator is 0. We want to make sure our denominator is not 0. And sure enough, that is, the first part is 0. Sine, each of these are 1. So we end up with 0 plus 0 all over 0 minus 2, which is 0. So the slope at pi over 2 is 0. Part B, working with the same equation of r equals 1 plus sine theta, we want to find where the graph has horizontal or vertical tangents. So using what we had up here, I'm gonna simplify this out. R dy dx is cosine theta sine theta plus cosine theta plus sine theta cosine theta. And the denominator is going to be cosine squared minus sine theta minus sine squared theta. We have a cosine sine and a sine cosine in the top. I'm going to simplify that down. There are two cosine theta sine thetas. Finding horizontal or vertical tangents. Horizontal tangents are when the numerator is 0, right? When we have a flat line. So I want to find that. I'm solving for when is 2 cosine theta sine theta plus cosine theta equal to 0. Where does that happen? Solving this equation, I'm going to factor out this cosine. We'll get cosine theta 2 sine theta plus 1 equals 0. And we get two expressions to solve. We'll solve for when is cosine theta equal to 0. And when is 2 sine theta plus 1 equal to 0. Cosine theta equals 0 at the top and bottom of our unit circle at the angles pi over 2 and 3 pi over 2. 2 sine plus 1 equals 0 when sine is equal to negative 1/2. Those angles, that's either here or here. Those angles are 7 pi over 6 and 11 pi over 6. So there is a list from 0 to 2 pi of the places our numerator is 0. Solving for our vertical tangents. Vertical tangents are when the denominator is 0, or where our entire expression for our derivative is undefined. So vertical tangents is where this whole expression would be undefined, or the denominator is 0. Taking that expression, cosine squared theta minus sine theta minus sine squared theta, setting it equal to 0. We want to solve this expression. Taking a look back at the horizontal tangents, what our first thing we did was factored. We pulled that cosine out. We don't have something that's the same all the way across. So if we can't have an easy factor, what we'd really like to do is make them all either sine or all cosine. We already have two that have just sine. So I'm going to turn that cosine squared into sine by using our Pythagorean identity. Remember, sine squared plus cosine squared equals 1, which means sine squared equals 1 minus cosine squared. So 1 minus, or cosine squared is 1 minus sine squared. Let me write out what I am saying. Cosine squared is 1 minus sine squared. So we can replace this cosine squared with that. Have 1 minus sine theta minus sine squared theta. Combining like terms, we end up with 1 minus sine theta minus 2 sine squared theta equals 0. This is a trinomial. We can look for if this factors. It does factor, and if you want to try the factoring yourself, think about how you would factor 1 minus x minus 2x squared. So, playing around with that ends up with the factoring 1 plus x, 1 minus 2x, and that is what we can apply here. The x's are really sine thetas, so we factor into 1 plus sine theta, 1 minus 2 sine theta, giving us, once again, two expressions to solve. One plus sine theta equals 0, and 1 minus 2 sine theta equals 0. Sine theta equals negative 1 happens at 3 pi over 2. Sine theta equals 1/2 happens at theta equals pi over 6 and 5 pi over 6. So now we have our list, but you may have caught something. 3 pi over 2 appears in both sections. Something cannot be both a vertical and a horizontal tangent, so we have to figure out which one it actually is. So we know dy dx equals r2 cosine theta sine theta plus cosine theta over cosine squared theta minus sine squared theta. And what we have just shown is if we plug in 3 pi over 2, the numerator will be 0 and the denominator will be 0. Both will be 0. We'll get a 0 over 0 form, and that's undeterminate. Can't be both a horizontal and vertical tangent. We need to figure out how to deal with this undeterminate form. So we're going to deal with L'Hopital's. So applying L'Hopital's, the limit as theta goes to pi over 2, 3 pi over 2, of our dy dx we apply L'Hopital's, we'll have that same limit, but now we take the derivative of the numerator and the derivative of the denominator. The derivative of the numerator works out to be negative 2 sine squared theta plus 2 cosine squared theta minus sine theta all over negative, the derivative of the denominator is negative 2 cosine theta sine theta minus cosine theta minus 2 cosine theta sine theta. Reminder that cosine of 3 pi over 2 is 0, and sine of 3 pi over 2 is negative 1. This is important because anywhere there's these cosines, these are going to 0. And anywhere there's these sines, these are going to negative 1. Sine squared would just be 1, and negative sine theta, sine being negative 1, negative of a negative 1 makes that plus 1. Making the numerator negative 2 times 1 plus 1. Negative 2 plus 1 is negative 1, and we get The numerator is -1. The denominator is 0. This is no longer that indeterminate form. Instead, we're getting an infinity. We're getting that the denominator is still 0. We're getting that this is still undefined, but no longer indeterminate. Meaning the denominator being 0 is what's winning. The numerator being 0 did not stay when we use L'Hopital's, making the question, is it a horizontal or is it a vertical? B, it's a vertical. The denominator won, the vertical tangent won. So our list is that for r equals 1 plus sine theta, the vertical tangents are at 3 pi over 2, pi over 6, and 5 pi over 6. And the horizontal tangents, 3 pi over 2 is not a horizontal tangent. So we have pi over 2, 7 pi over 6, and 11 pi over 6. And there are all the vertical and horizontal tangent locations between 0 and 2 pi. To get these r's, I only gave us the thetas. To get the r's, we would plug them back in and find the things like what is 1 plus sine of 3 pi over 2, or what is 1 plus sine of pi over 6. To plug those back in, to find r.